Next, we look at esterification. So for esterification, we'll only look at 3 out of our 4 functional groups. Because in general, amides are not able to be converted to esters. So we'll start with acid chlorides and anhydrides. And as with the previous reaction, these two reactions are basically the same thing. The only difference, whether we're using an anhydride or an ester or an acid chloride, is the leaving group. In both cases as well, just like with the hydrolysis, we can use a fairly weak nucleophile, just an alcohol, because the electrophile is so well activated in this reaction. So if we start with an acid chloride, we add an alcohol to it. The alcohol does nucleophilic attack. We form our tetrahedral intermediate. We lose a proton from our oxygen. And then the negatively charged oxygen re-adds its electrons back in, kicks out the chlorine, reforming our carbonyl and forming our product. And so as we've said repeatedly with these acyl substitution reactions, we're always going to see these same 2 steps. Nucleophilic attack onto the carbonyl to form a tetrahedral intermediate, and breakdown of that tetrahedral intermediate to form the product. And this reaction is no exception. We can also look at this reaction with an anhydride. As we said, with an anhydride, the reaction is going to be the same. The only difference in the reaction is the difference in leaving group. Again, we don't need to activate anything. We have a very good electrophile. So our alcohol attacks directly, and we form a tetrahedral intermediate. We lose a proton. And then that tetrahedral intermediate kicks out the leaving group, reforming the carbonyl and giving us our product. So again, 2 very similar reactions. Both have very strong electrophiles and therefore don't need any sort of activation of the carbonyl in order to proceed. One very, very common use of this reaction, especially in the case of the anhydride, is you can do this reaction using acetyl salicylic acid, which is this starting material, and you add acetic anhydride. Now the starting material has 2 OH groups, the OH from the carboxylic acid and the OH from the alcohol. And yet when you run this reaction, only one of those serves as your nucleophile. The OH from the alcohol is significantly more nucleophilic because the OH of the carboxylic acid has its lone pairs on oxygen tied up into resonance. But when these react, you'll form an ester between the OH of this alcohol and the anhydride, and the product that we form is this one, which is acetyl salicylic acid, or you may know it by its common name, aspirin. Now, the final group in this category of esterification is coming from esters. And at least initially, that might not seem like it's much of a reaction because we're trying to make an ester. But what we're going to look at here is known as a trans-esterification. And a trans-esterification is one where we can take one ester and convert it to an ester with a different R group. So this R group right here that I've highlighted in green, what we're doing in that reaction is we're actually changing that R group. And for those who are taking lab with me, you may recall or may see in the future, depending on how our calendar lines up, that we're doing one of these types of reactions in lab. In fact, the biodiesel experiment, where we're making biodiesel from waste oil, is exactly this type of reaction. We're replacing one R group on the ester with a different one. Now, this reaction usually takes place under acidic conditions and actually follows a very, very similar mechanism to the Fischer esterification. We start by the oxygen of the carbonyl being protonated, because again, we've got this weak nucleophile in the alcohol. But once we do that, that alcohol can attack and we form our tetrahedral intermediate. Once that tetrahedral intermediate forms, we get a proton transfer from the oxygen over to what was the ester group. That allows it to leave, and the OH group reforms the carbonyl, kicking out our leaving group. Finally, we lose a proton off of that oxygen to get us to our product. So if you compare this mechanism to the Fischer esterification, you'll see that the only difference between this and the Fischer esterification is that we have a carbon group attached to that oxygen instead of a hydrogen. Otherwise, the reaction is exactly the same. And so, just like with the Fischer esterification, equilibrium can be an issue in this reaction. And generally, the way that we control equilibrium here is by using an excess of alcohol. Same thing that we did with the Fischer esterification. In the Fischer esterification, we often use the alcohol as our solvent, and we do the same thing in this reaction.